All right. I'm Vitaly Zakuta. I'm a project manager. I have been a project manager for most of the IIIF effort at Harvard. And I'm going to start us off on our presentation about the IIIF infrastructure effort. First, let me introduce all of our presenters. I'm Vitaly Zakuta, as I mentioned, project manager. We also have presenting Katie Amaral, who has been a Scrum Master and a software developer, Doug Simon, and Chip Goines, who are software developers on this effort. There are many more software developers on this effort that are not presenting. It has been a large team, and I will mention a little bit more about the teams as part of this presentation. All right. So the effort to develop the IIIF infrastructure started back in the spring of the year 2020. Just a little history of Harvard Library and our infrastructure. We have been having images in our preservation repository since the year 2000. We have moved to our first iteration of IIIF and Mirador in 2015 with some page-turned objects. And in the year 2018, we have continued our implementation of the first version of IIIF, so that's version 2, and Mirador version 2 with still images. Our digital repository, the preservation repository, where up until very recently we housed both our preservation images and access images, has a lot of assets, over 7 million digital objects. Most of them are images. They have over 150,000 page-turned objects. They have thousands of audio files and videos. As of several years ago, less so in the number of files, but obviously a lot more in terms of the size footprint, the file size. In the spring 2020, as COVID hit, we started seeing increased use of our digital collections as everybody went online. We've seen increased use before, but it really skyrocketed as everybody was using remote teaching and remote learning. We had some performance issues that brought it home to us that it's time to embark on a project to modernize the IIIF infrastructure. It was also a good time to move to version 3 of the presentation API and also think about implementing Mirador 3. As that project was close to completion at that point. We also thought about decoupling our delivery assets from our preservation repository. As I mentioned previously, for almost 20 years, our preservation repository was both access and preservation repository. So we had files delivered from the same storage. Part of this project was to decouple this infrastructure and use Amazon, AWS, and other services that are more amenable to delivery of access files and have a lot of reliability in terms of fast delivery. Let me talk a little bit about project community. Our project community has included the Harvard Library leadership team. We also had stakeholders at Harvard Research Computing, Academic Technology, HarvardX, and Harvard Art Museums. We also had a Harvard IIIF advisory group involved in advisory capacity in this effort, and also consulted peer institutions and communities, including the IIIF community. Because this was such a large project, we have spun 2 teams of developers, each with its Scrum Master. We used a scaled agile Scrum model. We had project leads, business owner, project manager, project architect, interacting with both teams. And then we had a Scrum Master for each team, teams working in sync, meeting separately and having cross-team meetings. And that worked pretty well throughout the project effort. In phase one of our implementation, we concentrated on implementing the fast, reliable delivery. Asset and manifest ingest was Harvard Research Computing Academic Technology Department coming on as our first tenant of the multi-tenant infrastructure. And also implementing support for both IIIF version 2.1 and 3.0 presentation API. We also implemented persistent IIIF unique identifiers and worked on enhancing descriptive metadata that is being delivered with IIIF manifests. And also worked on implementing full text search and display for our IIIF objects, specifically the page turn objects, many of which have machine readable OCR. In phase two of our effort, we will work on implementing the DRS reference implementation. DRS is our digital repository service, as I mentioned previously. In this new iteration, the repository service will continue to serve as the archival storage. The delivery images will live in a separate AWS infrastructure and will be thus decoupled from preservation storage. We will also implement delivery of AV resources, which right now we are exploring for future implementation. And we will also work on implementing Mirador 3. Further out, we're thinking of implementing annotation tools and also rolling digital lending into IIIF infrastructure. Here's a little bit about our project milestones that have been completed so far. We've implemented the Cantaloupe image server that delivers images out of our AWS storage, the media presentation service, as we call it. We also added additional encoder to support not just JP2s, but also JPEGs, GIFs, TIFFs, and PNGs. And we built support for multi-tenant infrastructure so that other tenants can both submit manifests and files for asset ingest and use the API for delivery of manifests and images. And we also eliminated the use of custom legacy authorization layer and implemented IIIF authentication layer. As I mentioned, we decoupled the IIIF delivery services from our preservation repository and upgraded presentation API to support version 3. In terms of the enhanced descriptive metadata support, we have leveraged Harvard Library Cloud, which is a store that stores metadata, descriptive metadata, as well as administrative metadata. And it serves as a source for metadata for multiple library catalogs, and now will also serve as a source of metadata for our IIIF manifests. We've implemented the persistent IIIF unique identifiers and are in the process of implementing full text search with support for Chinese, Japanese, and Korean characters for searching. Next up, we'll be populating our solution with manifests. The images actually are already in our solution, so part of that is done. Next up is manifest ingest. We'll also start MVP acceptance testing with both the library and research computing, Harvard Academic Technology, and bring them on as our first tenant. After that, as part of the reference implementation for files that come from our digital repository service, we'll bring Harvard Library as our second tenant. I'm going to stop sharing my screen now and pass on the presentation to Katie Amaral. Just a quick administrative note that, well, please go ahead and type your questions in the chat, but we'll answer the questions after all of our folks and presenting, just to keep the flow.
Thanks, Vitaly. So I'm Katie Amaral. I'm a software engineer in Library Technology Services, and I'm on the asset delivery team for our IIIF redesign project. And today I'm going to be showing some architecture designs that we have for our system. So let me share my screen here. Okay. All right, so I'm going to start by going over some high-level architecture principles that have guided the design for the solution. After we do this, we'll start taking a deeper dive into the architecture designs and the decisions made there for how the architecture is designed and the technologies we use as well. So for our guiding principles, here are just a few of the high-level ones. So separation of concerns, where we're isolating our business logic into modular components. Don't repeat yourself, the DRY principle, so avoiding repetition, avoiding overlapping implementation of the same functionality. Single responsibility principle, so a single module or service has a single responsibility, and this allows us to avoid monolith modules and functions that are more difficult to maintain and update. And principle of least knowledge, so encapsulating the implementation details of a particular modular component within itself, and this allows us to have low coupling between components. So a single component, when it has the least amount of knowledge possible about the implementation details of another component, that avoids tightly coupled interdependencies. So from those guiding principles, we decided on a microservices model. So a microservice is simply just a small modular service that has a single responsibility and interconnects with different components in the system. So with the microservices model, we're achieving those principles: separation of concerns, single responsibility, and again, principle of least knowledge. Some examples that we will be going into a lot more detail are an asset lookup. So for example, that's just one microservice that's only responsible for lookups. The login app is a single microservice responsible for granting tokens. A converter service is a single microservice responsible for converting manifests. And we will get more into these individual services a little bit later. And here's an overview of the technologies that we use. For our languages, we primarily use Python with a Flask framework, and also JavaScript with the Node.js framework. For our image server, we use Cantaloupe. Databases, we're using Postgres and MongoDB for different purposes, and you'll see more about that later. And for our infrastructure, we're using Docker with Docker Compose. And to orchestrate and automate our Docker Compose and Docker Swarm, we're using Ansible. All right, so the components in our solution are generally categorized by resource type. So they're either a content resource or a description resource, and this is based on the IIIF authentication specification terminology, which distinguishes between content resources, and that refers to images or videos, and description resources, which refers to image API, presentation API, and the manifest services. A little bit more on categorization in the next slide. So we've referred to our solution as a media presentation services. And they're generally classified into categories by component types. So on the left, you see the list of component types. So we have asset ingest components, which we'll take a look at in more detail. We'll take a look at all these in more detail. Asset delivery component types, the manifest services components, and then we have another set of components for our DRS, our digital repository service to IIIF synchronizer. And again, that ties in with the concept of resource types, where we have content resource types for asset delivery and description resource types that refer to a manifest services. And again, this is more just conceptual and just how we kind of conceptualize and organize the components in the system. So the first group of components are the asset ingest components. So I'm going to go through and kind of quickly explain what these are, and then I will show a diagram that will walk through how it all works. So for our asset ingest component types, we have the Ingest API, which accepts ingest requests. We have our asset manager, which loops through the multiple assets in a request. One request could have one or many assets. So the asset manager loops through and creates a parent job to track those. We'll get into more detail in a bit. The task manager similarly creates the jobs to process the assets in the message queue, and also monitors and makes sure that the job is moving forward in the process. And if there's some issue with an individual worker, it'll resubmit the job and provide status updates as well. Our asset ingest workers perform the actual work for the asset ingest process. So the first step is validating to JP2 specification, and next steps after that are generating the thumbnails and also creating the asset records in the database. More info on that in a bit. We also have the manifest services workers, and we have a job tracker database, which stores the tracking information for the jobs that move along in the process. There's a list of steps that determine which order of the workers they're going to go through, and the job tracker database tracks the current status of the job, the step that it's on, any error messages that it encountered, and allows us to track the jobs as it moves along. We also developed several custom Python packages for the asset ingest process. So we have a job tracker Python package that we developed, a message queue utilities package that uses the STOMP protocol, and we have a job monitoring package as well. And that allows us to package up and easily reuse repeatable code throughout all of our different components. All right, so here I will show the first of many diagrams. So this is our asset ingest process. It's a big diagram, so I'm going to scroll in a bit here. So starting at the top left, I'm going to walk through this process. So starting at the top left, the requester service takes a set of JSON data that conforms to a particular schema that we have, and I'll show that afterwards. And the requester service also has a JOT token. I'll talk more about that later, but suffice to say for now that the JOT token provides access to the Ingest API. So the requester service takes that JSON data that conforms to that schema with a JOT token, a JWT token, and it makes a request to the Ingest API. And the Ingest API takes the token and it forwards the token along to the Authorization API, which is a separate, again, microservice. Each one of these little boxes, the dark thicker line boxes are an individual component. So the Ingest API takes the token and submits a request to the Authorization API here to just make sure that the token signature is valid and to get the allowed permissions for that token. We're going to talk a lot more about that later, Suffice to say for now, the JOT token provides access to the Ingest API. And then the Ingest API component does the schema validation and makes sure that the data in the request conforms to the schema that we're expecting. And then it then submits the request to the multi-asset manager component. In the meantime, it does send a response that the initial request was successful. Since this process is going to take some more time and goes through a queue, we send the initial response back with a job tracker ID number. So the asset manager, this component here, I'm highlighting, creates that parent job tracker document in our job tracker database. So that's this component here, the asset manager. It uses that job tracker package to create that parent job tracker document and update that job tracker database. And then from there, it will iterate each asset in the request. So it could be one asset, it could be many assets, however many assets, it will loop over. And for each one, it will send a request to the task manager. And what the task manager does is it creates the job monitoring timestamps for each job. So each asset gets its own individual job tracking document. And the task manager creates that child job tracking document, and that's linked to the parent job. So just stepping back for a minute, just to explain this a little bit more clearly, the asset manager creates the parent tracker document, updates the database, and then for each individual asset, submits a request to the task manager that then creates the child job tracking document. And the schema for the job tracker documents are the same. The only difference is that a child job will have that parent job ID as a reference inside of it. So that way we can easily query for all of the child jobs that belong to a parent job. So anyway, from here, the task manager, like I said, creates the tracking documents, one for each asset. And then it takes care of creating the job monitoring timestamp records as well. And then at that point, it submits the jobs to the queue. So each one it'll submit individually. And as I had mentioned before, we're using the STOMP protocol. There is a STOMP PI package that we use to communicate with the queue. So at that point, let me show a little bit more of this screen here. So it's kind of a big diagram here. Okay. So at this point, like I explained, our job tracking database has a parent job and child jobs. For each asset, it's going to have its own job tracking document. So going back down here to the bottom left, as mentioned, the task manager will submit a job, one for each asset. And then this oval shape at the bottom represents the message queue. So what happens is for each job that gets submitted to the queue, each job will have what's called a worker type property associated with it. And each worker has a configuration value worker type. And when a message gets dropped into the queue that matches the worker type in the worker's configuration, that way it knows, oh, I need to pick up this message because it's, I need to do something with this message because it has my worker type that I have in my configuration. So what happens is the first message gets dropped into the queue with the asset validation worker type configuration value set. And as I mentioned before, there's a list of steps that's pre-configured. And for each one of those lists of steps, we have the worker type. So it'll say step 1, asset validation worker type, step 2, image thumbs worker type, and then step 3, asset database connector worker type. So it's all based on that list of steps. So as mentioned, the worker will pick up the message from the queue, and each worker has a queue listener process running inside of it. I do have another diagram to explain a little bit more about that in a few minutes. But each worker has a listener running as a separate process, and then an API running as its own individual process. So what happens is the the listener process that's running in this container will pick up the message, and then it will call the worker API internally to perform the task. And the worker also uses the job tracker manager module to, again, update the job tracker database with the status of the job, again, for each asset, since each asset has its own individual job. So, yeah, the process moves along. So it starts with the asset validation worker, and this validates that the image is in an acceptable format and is in one of our supported formats. The next step is it goes through the thumbs worker, and it generates thumbnails for the image. And then the last step in the asset process is that the asset database connector worker then updates the asset database, which is a Postgres database, with the asset data. And again, each one then updates the job tracker document in the job tracker database. Oh, also, I should mention that the job tracker database is a Mongo database, and the asset database is a Postgres database. All right. So after the asset workers have all run through all the assets and all the asset jobs are completed, then the manifest gets submitted, and it goes back again through the asset manager to say that that parent was complete. And then it goes through the same process for the manifest that can be submitted with the list of images. And just to clarify, the asset ingest API accepts one or many images, and currently it'll accept one manifest, up to one manifest, but later we do have plans to support multiple manifests in the same request as well. All right, so the next set of workers it then goes through are the manifest workers to process the manifest that was submitted. If there was no manifest, then it would just do the asset side. But in this theoretical example, let's say there's multiple assets and one manifest, it'll process all the assets, and then it'll go ahead and then process the manifest. So similarly, the kind of mechanism to pick the message up from the queue with the listener is the same. Again, it uses that same package that we developed, the message queue listener package for that, and I'll talk more about that in a bit. But then it goes through our validator, converter, and then the manifest services. And Doug will be talking a lot more about this part, so I will just continue along for now. All right, so that is just an overview of how the ingest process works. Keep going along here. And I want to show a little bit more detail about how the individual workers work. So this diagram just shows the architecture of how we designed individual worker that listens to the queue. So this outer box here represents the Docker container that it's running in. And typically a Docker container is designed to run just one process at a time. But in this case, it made sense to run multiple processes in the same Docker container. So we're using Supervisor D, which is a process manager. And you just install Supervisor D and set up a configuration file. And for each process that you want to run with Supervisor D, you just provide the command to run that process. So what we've done is we have the Docker container start Supervisor D, and then Supervisor D starts each one of these individual processes. So this first process here is the message queue utilities package. So we have a custom package that we wrote for the message queue utilities, which uses the Stomp protocol and that Stomp Python package as well. And it starts up the message queue listener in one process. And then in a separate process, it starts, Supervisor D starts a Python Flask API. So when a message arrives in the message queue that matches the worker type configuration for this worker, the message queue listener will pick up that message. And once it receives that, it will call a certain handler based on the type of worker that it is and the category of worker that it is. And then it will call the Flask API endpoint. We have a genericized task endpoint. For that endpoint, there is a configuration value in the worker. So that way the listener knows what API endpoint to call. And this makes it easy because it can make a call just on the internal localhost inside of the container to perform the task. And that way we have the message queue listener running in one process and then the API running in another process. We don't have to worry about the processes blocking each other. All right, so that's how the workers work. Moving along. So our next category of component types is asset delivery. So I'll be showing a diagram for this in a second here. So we have an asset delivery component, which is responsible for coordinating the lookup and making calls to Cantaloupe. We have a policy lookup component, which is responsible for looking up the policy for the requested image. We have the asset database. We have the asset database cache. And of course, we have the image server. So let me pull up this diagram here for this. Okay. So this is a workflow diagram for a generic request for our asset delivery process. So a little bit different than the other diagrams that I showed. Each one of these columns represents an individual component, and each one of these boxes is just a step in the process. So a little bit different from the other diagrams we've seen so far. So in this example, starting in the top left, an image is requested from the viewer, and it would also work similarly if image is just requested from an embedded page. But in this example, image is requested from a viewer, and it goes right to our asset delivery component. So the asset delivery component then looks up the asset policy from our policy lookup component. In this particular example, we're assuming no token has been provided yet. And then the asset policy lookup will return the unauthenticated version of the policy because there is no token. And then the asset delivery will recognize that it needs a larger size than what was returned by the policy. So it'll recognize that it has to get a token for the restricted image. So what the asset delivery app does is that it then assembles a request to the login app. And the login app will validate the URL that's being requested. And this is referred to in the IIIF authentication specification as the origin parameter that gets passed in. So our login app will validate that origin, essentially. It will then coordinate the login to our Cav authentication system. And then once that login is successful, it then signs an access token that has access to content and description resources. It then stores the token in a cookie. This is this part of the diagram right here. You can see that circle is the cookie, and that diamond shape is the JOT itself. And then it redirects back to that URL that was validated with the original parameters that were passed in. So then it goes back over here to asset delivery. And then asset delivery takes the token out of the cookie and puts it in a header. And this is just for convenience purposes. And passes that token through the policy lookup again in the header. And then that policy lookup app then submits that token to the authorization service. So similarly from in the other diagram that I showed where the Ingest API forwarded the token along to the authorization service to check the signature is valid and to receive the allowed permissions. This is pretty much the same process that's happening here. The policy lookup is submitting that token to the authorization service to verify the signature and to verify that that token has access to the requested resource types that it is requesting. And also returns the stack of allowed permissions. So from there, assuming that the token signature was valid and the permissions were granted for access to the requested resource types, then the policy lookup goes ahead and retrieves from the cache the authenticated version of the policy. And then asset delivery recognizes that it does have access to the correct policy for the size that was requested. And then it goes ahead and makes a request to the image server. So as you notice here, we don't have the image server directly accessible. It goes through a series of other components. And then we have some internal networking to allow that one component to access the image server. All right, so that is the asset delivery process as an overview. And we'll dive into some more details here. Showed that. All right. So just a little bit more on the inner workings of our asset policy structure. So the policy itself is stored in the Postgres asset database. And the cache manager populates the Redis cache with that information. So that way the lookups are really quick and the cache is updated on a regular basis, and it is also updated on the ingest process. There is a message specifically for updating the cache that gets dropped into the queue as well. So let's see what else. So as we saw in the previous diagram, the asset lookup component looks up the policy statement from the cache. And the policy can be set at either the asset level on ingest, and this right here on the right is what it would look like setting the policy on the asset level on ingest. Or if it's not specified there, it will default to the account default level or space default level, depending on whether it's restricted or unrestricted. All right. So I'm going to show another diagram here for our data model. So this is the data model for our asset database. And as you can see, the table assets here, it has just some high-level information about the asset. And then also, if you notice up here at the top left, this is where we're storing our asset metadata. And the way we're doing this is a little bit of a hybrid model here, is that we have one asset can have many asset metadata records, and it's related by the asset ID. But as you noticed here, the asset metadata, the JSON value is a JSON object. And this made it a lot easier for us to store asset metadata in any kind of open structure that's needed. So you just specify the field name. So if you had just admin metadata or whatever you might have, and then you provide a JSON object for that admin metadata, and it's linked to the asset by the asset ID, Then we have, like I said, an open JSON structure that we can use for storing any various different types of asset metadata that we want easily. We went with that model because there's a lot of different types of structures that we need to support. So this was just having this open JSON structure was the easiest way that we could think of to do that. So that's the asset metadata. Also, as you can see, as we spoke about before, we have this policy table here. And the policy set is also a JSON structure. So it's that same JSON structure that we saw in the previous slide. And I can actually go back to that because I think I may have skimmed over it a bit. But this is the JSON structure for our policy. So we have, as you can see, we have an authenticated policy, and then a public, and then of course we have the thumbnail maximum sizes as well. So it's all based on whether it's authenticated or public, the default the policy for the image, or the policy for the asset, sorry, and then the policy for the actual thumbnail itself. All right, so back to this database here. So again, the policy table is a JSON structure with this policy stack that I showed here. And like I mentioned, the policy can be set on ingest, or it'll just fall back to these default policies that we have on either the account level. So there's a default policy, and there's also a default restricted policy, or the space as well. So there's a default policy here and a default restricted policy as well. All right. So that is overview of the asset database model. All right, so now we're going to get into authentication and authorization here. So this is another kind of category of components that we have. We have the authorization APIs we've seen a few times already. And then we also have the login app, which we talked about a little bit in the asset delivery diagram. We also have a custom module that allows us to integrate the login process with our Cav2, which is our central authentication system. And the solution uses a JOT token-based authentication. Okay, so the next few slides, going to be going over fairly quickly. The next few slides are just general concepts that will just help to explain later how the authorization API works. So I'm going to just quickly go over these general concepts here. So JSON Web Token is a JSON object that has three parts: a header, payload, and a signature. It's base 64 encoded, so it's not encrypted by default. The token is signed by either an asymmetric or symmetric key, and that signature is used to verify that the data is accurate and has not been modified. So it's used for data integrity. Just a couple of points to reiterate here that are important general concepts to know. So a signed unencrypted JOT is for data integrity only. The signature verifies that the data was not modified. A signed unencrypted JOT is not for confidentiality. So don't store confidential data inside an unencrypted JOT. The JOT must be encrypted for confidentiality. And there's a quick summary here from the jwt.io website, which I highly recommend if you're learning about JOT tokens. So a little bit more about symmetric and asymmetric keys here. So again, the token signature is for data integrity. So with symmetric keys, it's a shared secret key. So the same key is used to both sign and verify the token signature. With symmetric keys, there's no way to certify or differentiate the signer of the token since it's a shared key. The authorization API supports both symmetric and asymmetric encryption keys, and asymmetric is recommended here. When it starts going a little faster, just notice the time. So the asymmetric keys are a pair of mathematically related keys, public and private. The JOT token signature is for, again, data integrity. The private key is used to sign the token, and the public key is used to verify the token signature. So with asymmetric keys, the private key is the signing key, the public key is the verification key. And again, unlike symmetric keys, asymmetric keys also verify that the service that signed the JOT is authentic because the signer of the token is the only service that should have that private key. All right. So with all that kind of general information in mind, the Authorization API is a central service for verifying JOT token signatures. So if the signature is valid when a token comes in, the Authorization API will then return the allowed permissions for the token. Permissions are organized by resource type. All token issuers must be registered with the Authorization API. And again, the verification key is used to verify the signature. So with the case of symmetric keys, that's either the shared secret key, or in asymmetric keys, the token verification signature is the public key because it was signed by the private key, which should only be held by the issuer. All right, quick overview of the workflow. So a token issuer signs a token. The service that's requesting access to resources sends the token to the Authorization API. The Authorization API verifies the token signature with a verification key. If the signature is valid, the Authorization API looks up, confirms, and then returns those allowed permissions. And then it's the target resource itself that has to implement the access controls based on the permissions returned by the Authorization API. All right, another slide here on this, and then we'll move on to the other presentations as well. So another one of our components that we have is the login app with Cav2 integration. So the login app is a gateway, a login gateway that generates tokens after a successful authentication process. The login app supports multiple login types. It supports user login with Cav, a token login where you can provide a token and get another token, and it also will in the future support a kiosk login for a later phase. The user login process uses the Cav2 integration. The central authentication, Cav2 stands for Central Authentication Service version 2. The login app is a token issuer, as we talked about before, and the Authorization API, again, verifies tokens that the login app and other issuer services generate. So really, really, really quick, this is a diagram of the Cav integration process. And as you can see here in the middle, I'm skipping over quite a few steps here, but as you can see in the middle, this is where the JOT gets generated. It gets placed in the cookie, and then it gets sent back to the requester. Couple quick notes on cookies. HTTP only is true. That way it'll only be accessible by server-side code, and the domain should be set to the target domain so it doesn't flood other domains. Then also there is some caveats for your cross-domain cookies, but I won't get into that right now in the interest of time. So let's see, I believe that wraps up. Yep, showed that. Okay, so I believe that wraps up my part of the presentation. In the interest of time, I am going to pass it along to Doug, who is going to take the microphone. Doug, are you ready to start?
I'm ready.
Great, I'm going to stop my share.
All right. So I'm Douglas Simon, a developer at Harvard Library Technology Services, mostly working on the manifest services team. And I'm going to talk a bit about the manifest services part of our ingest process that Katie referenced a few minutes ago. So those particular components will be the IIIF validator, the IIIF converter, the IIIF services API, and the presentation public delivery, which is how the manifests will be delivered to most clients. I have a video demo that I am going to play of kind of the process playing out in a more manual way. And starting it now. My name is Douglas Simon. I'm a developer at Harvard Library Technology Services, and I'm I'm going to be walking you through the manifest services portion of our ingest workflow. Now, generally, these services will trigger step by step as they read from and drop messages off on various queues, but I'm going to be using their API endpoints to go through the workflow in a more transparent and manual way. So the first component, the manifest hits, is the IIIF validator. See here, we have a 2.1 manifest. And this component is largely based off the presentation validator community project. It contains most of the same logic wrapped inside a Flask application to which you can either post manifests or will validate upon receiving a message from the validator queue. So we will post this manifest, and what we're looking for is the OK1 response, which, despite the warnings, indicates that it is indeed a valid manifest. So when used as part of the ingest workflow, this will drop off a message on the task manager queue, which will move the manifest onto the IIIF converter, assuming that the manifest we were validating is version 2.1. Now, the converter is responsible for converting a 2.1 manifest into a 3.0 compliant manifest. And like the validator, it's also based on a community project, the Prezi 2.3 updater. Again, it's much of the same logic wrapped in a Flask app, and it'll respond to either post requests or to messages it picks up off the converter's queue. So we will send our manifest in, and we get a version 3 manifest back. So I'm just going to copy that for use a little bit later in this demo. So upon conversion, a message will be dropped off again on the task manager queue, and that will move both manifests onto the IIIF services step. Now, IIIF services is the name of our component that is what actually stores the manifests. They get information about them stored in a Postgres database, excuse me, while the manifest JSON itself is stored in S3 and cached in Redis. So I'm just going to go ahead and post this, the version 2 manifest now. Now, this response indicates that the manifest has been successfully stored in, again, the database, cached in Redis, and the manifest JSON itself in S3. So we're going to switch real quick over to my browser and bring up the manifest at this URL, which will be IIIF2, and then the manifest identifier, which, and this is coming from the Redis cache. So switching back here, we also have several admin routes where you can get information directly from the database about the manifest. We can get the content directly from S3, or we could do things like get the manifests for a particular account and space. So if we look, our new manifest will be in this list. Now, if you notice here, there are a lot of null fields. And that's because in our system, we do a lot more decomposition of 3.0 manifests than we do with 2.1. So now I am going to post the 3.0 manifest that we created earlier with the converter. Again, we have a successful ingest. Still do have a bunch of null fields, but that's because our manifest was missing a lot of these. But the important part here is we have this item count 1. Now, our database will decompose these manifests, and now we can get, for example, a list of all the canvases on that manifest. This will hold all the information about those canvases. And you can do the same with annotations, painting annotations, things like that. And lastly, our system will also support the ingest of collections. In IIIF services, the collections will be decomposed to show information about collection members in a similar way to what you're seeing right now with canvases. And all of them will be viewable to the public in the same way through the Redis cache. So the last thing I'll show you is just the version 3 manifest that we just sent in. And that's about what we got. Thank you. Right, I'm going to stop my share and I think I pass it off to Chip, who's going to be showing the assets in the viewer.
Chip, you're muted. We can't hear you, Chip.
Sorry about that. Can you hear me now?
Yes.
Okay, sorry. Again, my name is Chip Goines. I'm a software developer on the asset delivery team, and I'm going to show you everything that's the work that Kitty and Doug were showing and show it all together. I'm going to show you a generated manifest that's been posted against the manifest services. It contains an image with through the asset delivery pipeline and show that in the Mirador viewer. Hi, my name is Chip Goines, a developer at the Harvard Library, and I'm going to show you how generated manifests are loading inside a typical IIIF viewer. Here you can see a manifest that's been generated from IIIF services. And right here is the asset that's hosted within asset delivery. Below is the actual IIIF image API service endpoint, and it's a version 2 manifest. So to that, I'll take this URL, mirror to object. There it is. And in mirror 3, it's pretty much the same. Log the resource. Successfully. And that's how our image manifests are loading within IIIF viewers. Thank you. Thank you. Okay, I guess I will send it back to Doug.
All right, so for the next part of our presentation, I'm going to be running through a diagram of our IIIF synchronizer. Now, this system is going to be how we're going to be creating our manifests from our existing data in order to populate the service. So the first thing we have to do is make sure we have all the data we need to actually create the manifest. So we start with our pre-existing DRS, our digital repository service, which is populated with structure, image, and library cloud mods data. Upon insertion of new data or an update to existing data, we place a message on the DRS update queue. And just as a side note, in all cases throughout this system, the queue messages are pretty much just two types of IDs and a status property. So that brings us to our first new component, the IIIF bibliographic updater. And its responsibility is to listen to the DRS update queue where it picks up a message with an object ID. It queries the library cloud transformer, which checks library cloud for the mod's bibliographic data. If the proper record is found, it's sent back to the bibliographic updater and stored in the bibliographic Mongo collection. This allows us to have a complete set of data in Mongo and provides us with everything we need to build the actual manifest. So from there, upon completing that, the bibliographic updater places a message onto the synchronizer queue, which is picked up by the IIIF updater over here. The IIIF updater is more of a delegator than anything else. It's responsible only for listening to this queue and for sending tasks to a couple other components. For example, the IIIF assembler, which is next in the chain. The IIIF assembler's responsibility is gathering all the data from these four collections through a series of API calls. It does some formatting of it and sends it off to the resource builder. And the resource builder is where the logic of creating the manifest itself is largely contained. It pulls the data from the assembler and organizes it, formats it into a manifest and all of its components, canvases, sequences, ranges, annotations, etc. And assuming that the created manifest is valid, it gets passed back to the assembler and up the chain to the updater. And the updater places it into the ingest process that Katie talked about earlier. And yeah, that's about how we're going to be populating our system. And I think this concludes our presentation, and we can open it up for questions.
So it looks like there is one question in Huva from early on in the presentation. And it says, was there anything that you ran into that required much more or less investment than you had predicted?
Investment in terms of kind of time spent and complexity. I think there are some areas where we might have underestimated the complexity on certain things. I showed earlier a diagram of the worker prototype and how that works with the listener. That took some kind of creative solutioning to get that to be performant. And that's actually how we arrived at the Supervisor D solution, because our original approach to that was to use a multi-process module in Python Flask. But we were running into issues with that, some context issues with scoping, but also even just kind of getting the multi-process to work correctly, just generally. So that's how we arrived at the solution where we would use two separate processes in the same Docker container with Supervisor D. So that's one area that took a little bit more than we might have anticipated. And maybe also in terms of the job tracking mechanisms that we were showing before with the asset ingest pipeline. We originally kind of started with a simpler model of just one tracker per job, and then we arrived at a kind of parent-child model, and there were some kind of iterations of that. And then we arrived at the model where we have a Mongo database and one document representing each job. And then we still kept the concept of the parent job to track the status of all those child jobs in the process. So I think that's another area where we kind of had a simpler solution at first, and then it just started to evolve as as we kind of got deeper into the solution. So, so yeah, those are two areas that come to mind. Any other questions or?
There is one more. Was there anything you ran into that required, sorry, that's the one we just asked. Do you plan for text search and search API implementation using ACO? Oh, wow, it's near the end of the day. Using OCR files like Alto or HOCR?
Yes, we have plans for that in the works. We have our full text search solution, which is in the process of being updated. And then we have some work scoped to import our OCR text files into our Solar system. And then that will allow us to implement OCR within our FTS search. There might be somebody else who can provide more context with that.
There are some more questions.
Sure.
How does someone with material to be ingested into the system enter the queue? Where is the front door for material to be ingested, assuming that manifests, canvases coming in for, assuming manifests and canvases are coming in from a variety of sources at Harvard?
Yep, great question. So the kind of front door for all of that is the Ingest API. So any service that's requesting, that's sending requests to the Ingest API will need to be registered with the authorization service. And then once that service the requesting service is registered with the authorization service, then they will be able to generate tokens. And so they'll need to be able to generate a token that has access to the Ingest API. And then once they have the token, then they'll be able to submit requests to initiate ingest of manifests and assets as well. Hopefully that answers that question.
Great.
Glad to provide more detail.
There's one other question and a comment. Thanks for a really good overview. Lots of takeaways for me for our upcoming systems redesign. Thanks. Were there any particular challenges you faced with using so many microservices? Once something got pushed into the job queue, where did the responsibility lie for dealing with failure?
Okay, great. That sounds like two distinct questions. So I'll answer the first one first. I think with microservices, you really need to have strong standards with how you're going to design your services. So for example, if you decide that you're going to use Flask APIs, you definitely need to have strong standards and prototypes for how you're going to implement that. As you can imagine, there's a lot of implementation details that you can't avoid repeating. For example, like logging and just setting up your basic API routes and your Docker container and the image, the Docker image for that. So, so yeah, I think that's one area where I would say, ran into some challenges with just making sure that we had strong standards, and which kind of evolved along the way a little bit, just naturally as we had to kind of adjust and add things in. So I'd say that's definitely one of the disadvantages there, is that there's kind of some unavoidable repetition that you have to do with setting up the basic administrative like logs and things like that. So yeah, I'd say strong recommendation would be to make sure you have strong standards and prototypes for your microservices ahead of time, which we did, to a good certain extent, but I think it was also one of the challenges kind of as the project evolved. But yeah, great question. And then the second part of the question in terms of the responsibility for managing the job as it's moving along, I think the question was, or when it completes. That's the task manager's responsibility. So there is a package that we developed for, that's a set of job monitoring utilities. And that package runs inside the task manager, and there's a list of jobs that are in progress. And there's a timestamp that gets updated in the job tracker database. And we have configurable timeout windows. So if a particular worker isn't responding within a certain configurable time window, then the job monitor will go and restart it. Also, in terms of handling failures, obviously there's going to be situations where there's a failure along the way that isn't because the worker's down, and that is tracked in the job tracking database as well. We have a structure to handle errors. So anytime an error is encountered during the process, that gets added to the tracker document. So we can see exactly where it failed in the process and which worker it stopped on. And then also there is a mechanism to roll backwards. So not only we have a standard API endpoint for performing a task, but we also have a standard API endpoint for reverting a task that a worker does. So when it's going forward and then it hits an error condition, if that error condition is set to roll back the workflow, it'll revert. So the workers will then go backwards. There's some workers that will need to, roll back the work that it did. Other workers, it'll just pass through and roll back. And yeah, as I mentioned, every error along the way will be tracked in the tracker document. So yeah, so hopefully that answers both of those questions adequately.
Fantastic answer. Thank you very, very much.
Thank you. You're very welcome.
So going back to the question of, let me find it here, where is the front door for material to be ingested? Mm-hmm. The asker had clarified that they meant who should someone with manifests or canvases contact for ingest. They're looking for a person or persons to connect with.
Oh, okay. So I suppose, Vitaly, would that be
sure.
You as a representative of our group, or?
Well, actually, Stu has answered that in the chat, but I'll repeat it. I'll repeat the answer. So basically, as he mentioned, the audience for these particular systems are implementers, but there are different front doors. One front door would be the deposit of the content into our digital repository. That's part of the library front door. We may in the future implement something like a Nextcloud file sharing platform. Both folks can stage things. Another front door in partnership with Harvard Research Computing and Academic Technology Services would be the Canvas, which is the course platform. So folks would stage files, images through Canvas, and then there'll be a process under the hood that will ingest it from Canvas to the multi-platform solution that we have developed. So those would be some of the front doors.
Great. And one final question along the same theme, following up on the front door question, how does a non-technical person start something in the queue? It sounds like your system connects with other developers throughout Harvard.
Right. So the media presentation solution will take things into the queue from other systems. So for a non-developer, if it's, for instance, a researcher at Harvard, a faculty member, they would probably get in contact with Academic Technology Services, Harvard Research Computing, or librarians, which would then shepherd them to stage their content in various ways, whether it's in Canvas or in our digital preservation repository. And then the content will make it over to the delivery solution.
Are there any other questions for the group? Sounds like maybe no. All right, great. Thank you all so much for this presentation. It was really wonderful to see all the work that you've done. It was great to see everyone on the call. If anyone has any questions or wants to follow up after the session, you can, of course, continue talking to folks on the Whova platform throughout the duration of the conference. So thanks again. And just a reminder that this is being recorded, so we'll be able to send it out afterwards if there was anything you missed.
Great.
All right. Thank you all.
Thanks, everyone.
Thank you.
Thank you.
Bye.
Thank you.